Hello, so in this video I'm going to introduce stoichiometry, and that is how you spell it, and it's pronounced stoichiometry. So it's a really complicated sounding word, but it actually represents an idea that's really simple and really straightforward, which I'll hopefully demonstrate in a second. The definition of it though, the one that we're going to use in our class, is it's the relationship between the amounts of reactants and products in a chemical reaction. And that's very vague and very general, and that's actually going to be okay for us for right now. So it's the relationship between reactants and products in a chemical reaction. So what does that really mean? Well, if you imagine taking two pieces of bread, some peanut butter and some jelly, and you're going to make one peanut butter and jelly sandwich. So your reactants are the things that you start with, products are the things that you end up with. And so really you have enough materials to make one sandwich. So if you need to make two sandwiches, you need to double the amount of reactants or the ingredients. So same idea with baking. If you bake brownies and you need to double the batch of brownies, then you double the ingredients, or you buy 2 boxes or whatever. So really that's the big idea with stoichiometry. It doesn't get any more complex than that. It's just the relationship between reactants and products. Actually, I lied, it does get a little bit more complex, but we'll gradually show you that. There are some big ideas that you need to remember, and some of them you'll need to learn too, but conservation, the idea of the conservation of mass, matter and energy, you can't create those, you can only convert between one form and another. Moles we'll talk about in this video, and then balancing equations you've already done. And actually, even though we didn't really explicitly say it at the time, balancing equations and reactions in this way, in the way that we've done, involves stoichiometry and is stoichiometry. So the good news is you've already covered it quite a lot. So we're just attaching this term to it now. So let's look at an example. We've got H2O being formed, water. We've got one hydrogen molecule, which is made up of 2 atoms. Same idea with the oxygen, and it produces 1 molecule of water. So the idea of the conservation of matter law is that we can only have the same types and the same number of atoms that we have on both sides of the arrow. So if we have hydrogen and oxygen, we can't have any other element as a product because it's not as a reactant. So that's the idea of conservation of matter. We also need a certain number of, equal number of atoms on both sides. And that's the idea of balancing equations. So if we were to balance this, we did it this way, which is still a good method. So you list out the reactants and the products. We've got 2 hydrogens, 2 oxygens. On this side, we've got 2 hydrogens and 1 oxygen. So you balance one line at a time. The hydrogens are balanced, which is good. We need to double the amount of oxygen. So if we do that, the only place that I can put a number is at the front, kind of like a coefficient in algebra. I can only put a number at the front, which means I'm multiplying everything after it by 2. That doubles the amount of oxygen, but also doubles the amount of hydrogen. So then I need to go back here and change that to a 4 and put a 2 right there. So this would be 2 multiplied by 2 gives me 4, 2 oxygens, and this is all balanced now. So this now obeys the conservation of matter law. It also obeys the conservation of mass law. If I start with 100 grams of reactants, then I must end up with 100 grams of product. And once you know that law, that's stoichiometry. That's the big idea behind stoichiometry. We're really looking at the amounts or the quantities of reactants and products. So whatever you start with, if it's 100 grams, 2 pounds, 1,000 kilos, you end up with the same amount as a product. Okay, so let's go back and look at this idea of moles. So I'm going to erase this for now. So the idea of stoichiometry is it's very helpful. because if we know that what we start with we should end up with, conservation of mass law, then we can figure out how much of a particular reactant we need for a reaction. If we start with a certain amount, say for example the hydrogen and oxygen example that was just on the board, if we start with a certain amount of hydrogen, we can calculate how much oxygen we need to get a certain amount of water. And so industrial chemistry is based around this, calculating how much of each reactant you need to get the maximum amount of product. Also, I suppose if you're making crack as well, then that would be really, really helpful. So if you know exactly how much you should get, and if you don't get that, then obviously your process isn't good enough. Okay. And so we've looked at balancing equations, and we really looked at one, or maybe one molecule at a time, or small numbers. We didn't really think about it on a much bigger scale. And obviously atoms are really, really tiny. Molecules are really tiny as well. So we need a system, we need a practical system that's going to allow us to measure out quantities of an element. And that's what I'm going to explain next. Before I do that, let's look at an idea. And I was looking through my desk this morning. There we go, paper clips. 100 paper clips are supposed to be in this box, so it got me thinking, well, is there some person on minimum wage counting out 100 paper clips every time? How do they get the paper clips 100 every time inside a box? Because if they put 100 on the front, then it's got to be 100 when the consumer buys it. So how do they do that? Well, the way that they probably do it is very similar to how we'll use stoichiometry, and how I'll demonstrate that in a second. But if you figure out how much one paperclip weighs, and then you multiply that by 100, then you can just measure by mass. So if you know, obviously that all the paperclips need to be the same size and the same mass, but if you know how many 100 paperclips weigh, you can just measure out that mass every time. So probably, rather than just counting 100 paper clips or some special device that measures 100 tricky little shaped things into a box, probably a lot easier just to have this on some kind of scale and then dump in 100, and then you're done. So the idea of counting by weighing is the idea of the mole, which I'll go into a bit more detail. So just to emphasize this point, we can figure out we could easily measure out 2 million paper clips. If we knew what one weighed, we could weigh out 2 million paper clips without counting out each individual paper clip, which would be a giant pain in the you-know-what. So that's the big idea of chemistry, because we need some system that allows us to measure out quantities that we can work with in a laboratory without weighing out individual atoms, which is really, really challenging. Okay. So we need to go and cover a basic idea called the atomic mass unit idea, which we haven't really talked about too much. But it gets back to the idea, and it's shortened AMU. It's getting back to the idea of a practical system to measure things, and also a consistent system worldwide. So it's used everywhere, and everyone follows the same system. So the definition of an atomic mass unit is, or 1 AMU equals 1/12 the mass of a C12 atom. So carbon 12, this isotope of carbon is used because it's got exactly 6 protons, 6 neutrons, and 6 electrons. It's also really common, really easy to find and cheap. And it's a stable isotope. Carbon 12 is stable. So the definition, the overall system that we use that's going to lead us into the moles in a little while, are atomic mass units. The definition is 1 AMU is equal to 1/12 the mass of one carbon atom. And if you think about what carbon atoms are made up of, electrons, protons, and neutrons, 1/12 of the mass would be the mass of one proton, or the mass of one neutron. And that has a special value, and it's 1.66 times 10 to the negative 24 grams. Obviously, this has been measured. This isn't just some theoretical idea. This is a definite value. This is a definite amount. We know how much one proton weighs. And so this is the general system. So 1 AMU is equal to this many grams. And the definition of it is a 12th of the mass of a carbon atom, which is basically the mass of a proton. P plus, proton, n to the power 0, neutron. All right then, so is that helping us get to where we can use a system that can measure out certain amounts? Well, yes and no. So there's a bit more explanation, but just to introduce this idea, and hopefully you'll take notes and write this down, because I'm going to erase it right now. But it's building up to this idea of the mole being able to weigh out a certain amount of an element or a molecule or a bunch of atoms. So as we move into stoichiometry properly, we can't avoid this gentleman. It looks like avocado, but it's actually Avogadro, very famous Italian scientist from the 18th century. Late 17th, early 18th century. The idea of Avogadro, I almost said avocado, is that he developed an idea from another scientist called Gay-Lussac. So this gentleman's ideas about atoms and atomic theory were that when gases react with each other, they do so with small whole number ratios. So that example of hydrogen and oxygen combining to form water, it was 2 hydrogens, 1 oxygen molecule forms 1 molecule of water. So it isn't 1.5 molecules of one thing and 0.25 molecules of another, it's whole number ratios. So this idea of his was developed by Avogadro, who theorized and measured and did some more chemical reactions with hydrogen and oxygen and forming water. And he said that what did he say? All right, so he took this idea one step further, and his idea was that if you have 2 volumes or 2 amounts of gases, they're at the same temperature and the same pressure, then they'll contain the same number of atoms or particles or molecules, whatever they're made up of. So this is not necessarily related to the mole yet, but Avogadro's big idea was if you have, say, a liter of hydrogen gas and a liter of oxygen gas, there'll be exactly identical numbers of molecules inside those 2 containers, developed from this gentleman. So, not that he's not important, but we're just going to erase him for a second. So Avogadro had that idea. As chemistry developed and became more advanced, electricity came along, and then the electron was discovered. And then a scientist called Millikan and Faraday, they eventually gave us an amount based on Avogadro's hypothesis, or theory, sorry, so they could calculate exactly how many atoms and/or molecules were inside a certain volume. So it went from being a theory to an actual definite calculated amount, or measured amount, excuse me. And so Millikan, he discovered the mass and charge of an electron. Faraday took it one step further. Both theories worked on each other to come up with an exact number in a certain volume of gas. And so that we needed one number. Chemistry needed one number. And so there's a very special number called Avogadro's number, or Avogadro's constant, it's sometimes called. And the idea is the mole idea. So 1 mole equals this many of something. So it's kind of based on his theory, but he didn't discover this number or calculate or measure this number. Other people did, but this number is named Avogadro's number for his contribution to stoichiometry and chemistry in general. So 1 mole is the concept that we're going to be looking at. It's always the same number. So in the same way that 1 dozen of something is always 12, or a pair is always 2, or a score is always 20, 1 mole is always this number. So if you have a mole of atoms, it would be this many atoms. 6.02 times 10 to the power of 23 is a huge number. And if you think about it, that makes sense, because you need a huge number. You need to measure out a huge number to actually get a mass that you can actually deal with in a laboratory. So 50 atoms wouldn't give you a reading on a scale. 1 billion atoms wouldn't give you a reading on a scale. You need a much, much bigger number. And this is a huge number. This 6 with 23 zeros after it roughly is the scale that we're dealing with. It needs to be a big number because atoms and molecules or particles are so small. So if you think about, if you only have a scale that measures in kilos, and you put 1 paperclip on that scale, you're not going to get a reading. You're going to need a lot of paperclips to get a reading on a scale that's measuring much bigger quantities. Same idea with this. You need a big number of atoms or molecules to get a reading on a scale in order to be able to work with it. So that's this number. It's been measured, it's been calculated, it's a worldwide standard. 1 mole is always this many of something. Whew, it's exciting. So if you have a mole of carbon, let's say C12 atoms, then you'd have this many atoms, 6 times 10 to the power of 23. So if you have a mole of carbon 12 atoms, that's how many you have. If you have a mole of iron atoms, that's how many you have. If you have a mole of oxygen molecules, that's how many. I'm labouring the point somewhat, but it's always the same. Same idea of 12 always being the number of a dozen. This many equals 1 mole. So there's a definition of the mole, and it involves carbon 14. Again, carbon's just used as a good standard substance, stable molecules. So the definition of a mole is that so it's the amount of substance same amount of substance in 12 grams carbon 12. We'll use the definition of a mole to be this many. This is just the actual chemistry definition of 1 mole. It's the same amount of a substance that you would have in 12 grams of carbon. So 12 grams of carbon is exactly 1 mole, and it contains that many atoms. So let's rewrite that. Oops. So 1 mole of that this type of atom gives you that many atoms, and then that has a certain mass, and it's 12.0 grams. So if you look on the periodic table, that number doesn't match. The number on the periodic table is actually 12.011, I believe, grams. And that's because of the isotope idea. The carbon has 2 isotopes, 2 stable isotopes. Carbon 12, well, carbon 13 isn't stable, it's radioactive, but it's around long enough where you can actually measure it out. Its half-life's like 5,000 years or so. But you take an average atomic mass, so that's why it's not exactly 12.0. There's another isotope of carbon. But if you want to weigh out 1 mole of carbon, let's just go crazy and say, I don't want to weigh out 1 mole, I want to weigh out exactly this many atoms. Well, then you'd get a scale, you'd get your carbon, and you'd put 12.011 grams on there. That would give you exactly 1 mole and exactly that many atoms. So we're going to fix this. So that's the number that we're going to be dealing with is Avogadro's number, and it's always the same number. It's related to this concept of moles, which is really just a really convenient way for us to weigh out quantities of something. If whether you're using a small scale like nanograms or even bigger like kilograms, knowing this information that's already been calculated and measured and on the periodic table is really, really useful. So we don't need to do that work. So the definition, another definition that we're going to be working with is molar mass. And that's actually pretty straightforward. It just means the mass of one mole. So carbon was one value. Let's say that you have sodium chloride, and you wanted to know the molar mass, and you wanted to weigh out 1 mole. Well, then you'd look up sodium on the periodic table, and chlorine is 35.45 grams, or 1 mole of it would weigh that many, and sodium is something, I can't remember off the top of my head, that's embarrassing. So anyway, you'd add them up. So let's say it's 23 grams. So if you added those up, you'd get 55.45 grams, and that would be 1 mole. Actually, so grams per mole. So the shortcut, or the units that we use, there's that many grams in 1 mole, or grams per mole. So now that we know this, we have a really nice system. So if we wanted to weigh out 1 mole, we'd just weigh out of sodium chloride, we'd weigh out that much. But what if you wanted to weigh out a fraction of 1 mole, like a half a mole, or 0.25 moles, or something like that? Well, you'll be very pleased to know that there's a little system that we're going to use, and it involves some math. Nothing too crazy though, but I'm going to show you that in the next video. Just to recap some of the big ideas in this video about stoichiometry. It's a big sounding word, complicated sounding word. It just means the relationship between reactants and products in a chemical reaction. Think peanut butter and jelly sandwich, 2 pieces of bread, a dollop of peanut butter, a dollop of jelly, it makes 1 sandwich. If you want to double how many sandwiches you have, then you double the ingredients. If you want to triple it, you get triple the ingredients or the reactants. Stoichiometry involves some big ideas, balancing equations, which really is this idea of conservation of mass and matter. So if you start with 100 grams of reactants, then you'll end up with 100 grams of products. The number and type of elements that you have, or atoms that you have, must be the same on both sides of the arrow. You can't just magically create an element in a chemical reaction. You need a nuclear reaction for that. Chemical reaction isn't going to involve that, creating a new substance. This idea of the mole, it sounds crazy complicated perhaps once we introduce some math into it. Think of it as a dozen, right? A dozen is always 12, 1 mole is always the same number. It's a much bigger number, but we need that bigger number because we're weighing out tiny things called atoms and particles and ions and that kind of thing. So we need bigger numbers for that. And so that's stoichiometry. So where we'll go next is looking at some more practical uses of the mole, and that will involve calculating fractions of moles, weighing out moles of a compound, of a molecule, and making it really, hopefully, very practical. And that's it.